All right, so extinction. Organisms have gone extinct since organisms existed. And um, we have an extensive record of this. The fossil record documents that organisms have gone extinct over and over and over again. And so one of the questions that people have is, extinction is normal, so why on earth should I be concerned? And the thing is that currently the extinction rate, or those organisms that are basically committed to extinction, even if they are not extinct yet, is so high that it is at a rate that is unprecedented in normal times. So let's go talk about the extinction rate and what happens under non-normal times. All right, so what are we talking about when you hear conservation biologists sounding the alarm about extinction rates being too high? Well, in the past, we have had a series of what biologists call mass extinction events. And when we're talking about mass extinction events, these are events in which at least 75% of the existing species go extinct in a 2 million year period. So there's a radical loss of species on Earth during these events. And you can see they result in radical drops. That's what the arrows represent in this image here. Okay, these events can happen, for instance, when an asteroid hits the world and changes the climate radically, very quickly. And that's what happened when the dinosaurs went extinct, for instance. So these sorts of events are massive. They cause a significant amount of death and suffering at the time that they happen. These have happened in the past. They've happened 5 times in the past. They have been major events that have radically changed the course of history, of evolutionary history, when the Earth recovers out of it. So that's what we're talking about, that extinction does occur on a regular basis, but it's occurring more right now. And I'm going to show you some evidence for what's happening now. So here's an example of a graph that we've created, and it looks at, sorry, I'm just trying to turn on my drawing tool. So it looks at species area curves, like we've shown in previous lectures, but it shows them for 2 different time periods. Time periods before humans arrived and a time period after humans arrived in North America. And what you can see is that in North America, it didn't matter where you sampled. The larger the sample you select, the more mammals you're going to see. When you're looking, where are we looking? This animal is clearly not something we see around right now. This is in the fossil record. And so you can see that there is a positive linear relationship between square kilometers sampled and species richness. What's interesting is that when you look during the time period after humans arrived, you can see that the line is lower. That means that there have been some species that have been either wiped out or radically declined in their abundance, such that they don't exist in some locations, right? Because you have to sample them in your sampling along this log scale. They no longer have the range that they used to have before humans arrived. So humans can have a significant and negative consequence for mammal abundance in North America. When we start looking around the world, it's interesting to notice how many species are at risk. When we start looking at all the conifers in the world, all the conifers in the world, 34% of them are threatened right now. And another 16.4% are almost at the status where we would consider them threatened. That is, they're now rare, but they're not at the point where they are precipitously rare. For birds, we see that 13% of them are threatened, and another 9% are near threatened. Reptile species, there are 24% of all reptile species are threatened, and another 7.8% are near threatened globally. Amphibians, oh my goodness, did you guys see this? 42% of amphibians today are threatened because they are so rare. And another 8% are near threatened. That basically gets us to 50% of amphibians on this planet are threatened. There are some radically tragic stories happening here, right? 25% of mammals on Earth are threatened, and another 7.5% are near threatened. Fish, 18% are threatened, and another 4%. These are radical numbers. And when we start thinking about extinction criteria, right, for mass extinctions, with amphibians and conifers, we're getting to the point where we're not at 75%, we're at 50% of their species are on the brink of extinction. That's essentially what that means. That without any action, they will go extinct, and we've reached the threshold for defining a mass extinction for at least conifers, amphibians. This is not the trend we want to go on. Now, remember that we've talked about how net primary productivity is related to species richness. Here is another illustration of basically the same idea. On the x-axis, we're showing you species richness, and on the y-axis, we're describing above ground biomass. So that's how much planty stuff and animal stuff is above ground. And we're looking across a whole pile of European locations. And I think what's interesting here is basically this suggests that the more species you have, in general, you see greater ecosystem function or more above ground biomass. Now, it's not always. Look at Greece. Greece has no relationship between species richness and above ground biomass. So this is definitely not, this is counter to everything else, but generally there is a positive relationship. Again, Ireland's also really interesting to see that there's not an increasing above ground biomass after a certain number of species, but generally that's what we see. So this is another reason why species diversity or biodiversity in a particular location is going to be useful. We're going to see more ecosystem function, more above ground biomass, more green stuff if we have more species. Now, this has led to us to think about a whole pile of genetic diversity, a whole pile of biodiversity within the world as valuable. And here's an example of this is not only are we talking about species diversity in the world, but we're also talking about genetic diversity. So here is a sampling, and this is not a complete sampling, but just a sample of diverse chicken breeds that we have here in the world. And you can see that they all have weird and wacky things going on with them. They all look radically different. But these are all chicken breeds that have been bred because there is there's the opportunity to do so. And we have this treasure of genetic diversity in here. Now, we see a whole pile of different phenotypes here, and these different phenotypes will have different economic values. But I think what's also interesting is that correlated with all these different phenotypic traits, we will see different levels of disease resistance, different levels of ability to deal with dry situations, drought, food shortages, etc. in these chickens. And so by preserving the entire genetic range of chickens, we may be able to, without knowing it, prepare chickens to be able to deal with future challenges that are yet unknown. And so this diversity that we have right now, whether it's biodiversity as species richness or genetic diversity, is valuable in some ways for a future instrumental use as well. We also see a radical genetic diversity in crops as well. I think I spoke to you in the fall or in botany about genetic diversity in corn. This comes out as, the corn that is well bred. We have the wild relative teosinte. This is the kind of research that I've been thinking about for a long time, is what happens when you mate a wild relative and a crop together. I don't think about corn, I do it in radishes, but the same idea. And you can start to understand, for instance, how traits in corn are inherited. When we look around at corn cultivars around the world, and in particular here in North America and South America, well, Central America, Mexico and Southern US, we see the diversity of corn is really, really high. And this is because the center of maize diversity, or center of corn diversity, is in Mexico. And so we start to see diversity among plants. We also, in some cases, see diversity among seeds. So you can see these different colored kernels. They represent seeds that have different genetic signatures. They have different genetic signatures for seed color. And so it's kind of fascinating to see how there's all of this genetic diversity that can be stored within a plant, within a cultivar, and within a species. And all of this is incredibly important to conserve. Now, I think I mentioned this in botany. One of the ways in which it's incredibly important, we believe it is incredibly important because it will, crop diversity that exists today will help us solve future environmental and disease challenges. And so researchers around the world think it is so important that we have set up seed banks where we store seed that is representative of a particular cultivar in a bag that is heat sealed and vacuum sealed. That bag is then stored in a box, a storage box. That storage box holds up to 500 different seed packets, and those seed packets are then stored in a vault. And the vault holds hundreds of boxes. And we have many, many vaults. The vaults are found within a concrete-lined cave that is constantly held at -18. And this vault is located under the ocean in Svalbard. And so we call it the Svalbard Global Seed Vault. Researchers from around the world send their seeds to the Global Seed Vault, and this serves as a backup in case a disease ever wipes out all of the seeds on Earth of a single species. We can eventually, if we can figure out how to control the disease, bring the seeds out and restart that species of crop. So we've spent a lot of time, we understand explicitly how to conserve seeds, especially of crops, but we rarely do that for non-crop organisms because we don't have the financial resources yet for that, frankly. All right, with that, that's the end of this module. Pretty stiff situations. So with that, I'm done my lectures for this week. I hope that you find some ways to rest and relax this week. And if you're listening to this on the Thursday when it's due, I hope that you find ways to relax and rest the following week. Okay? All right, take care. I look forward to conversations with you. Bye-bye.